Alright, so I believe one class got to, I don't believe your class actually got to the example problem. So this was try on your own. I told Austin to stop talking, so sorry about that. So that's really not applicable to one class, but it's applicable to you. This is an example from the book. It says an ordinary six-sided die is rolled once. Determine the chances of it getting 6. Well, that would be, yes, of course, the probability of 6 happening, because 6 is the event, and we now have 1/6 because we do the probability of the event over the probability of the universal set, correct? Oh, just to mention, here's our sample space. So we can write a sample space for basically anything that we get. We can see the probability of not 6. That means it's the probability of 1, 2, 3, 4, and 5. Now, I said this to one class, but I just want to make sure that you are clear that this OR right here means basically addition. Okay? The OR means addition. So we are saying 1 or 2. That means we are taking the probability of 1 and adding it to the probability of 2. And that means that we get 1 over 6 plus 1 over 6, which is 2/6, and the book decided not to reduce, but that should be 1/3 is your probability. Okay? Alright, same thing goes with this. If it's not 1 or 2, it's going to be 3, 4, 5, or 6. So with this OR, that means we are adding 1/6, 1/6, 1/6, and 1/6. Is that clear? Okay. So you can reference that in your book as we go on. So next we're going to be talking about complementary events. Okay. Complementary events are two events two events are complementary if exactly one event occurs, exactly one of the events must occur. Okay, so if A is the outcome, then we say A, not O, but A prime is the complement of the event A or not A. So basically what it's saying is that for everything that we have A, there is also the not A. Okay? So this, if I was to write it out in words, it would be like A happens. We have the probability of A. And A doesn't happen. That's the probability of A prime. Okay? And if you add these two up, we end up getting the entire universal set. Oh, great. I forgot I'm recording and now there's a fire alarm. Oh, if that was it, then that's not bad. It's funny that they did that. So A prime is just not A. Okay? So if we go back to that example that we just saw up here, we have not 1 or 2. That would be kind of the example. So let's actually take a look at this one. This is not 6. So if A is 6, then A prime would be not a 6. It's everything else. Because if you add those two up, 1/6 and 5/6, you end up getting 1. So those are called complementary events. Okay? So here's another example. Oh, did you want to write that down? Okay. So if you want to reference previous slide. That would be good. You don't have to write that. I am going to talk about complementary events as an example. So this right here, this complementary event definition is in your book as well. So I'm going to move on. Using a two-dimensional grid to illustrate the sample space for tossing a coin and rolling a dice simultaneously. Okay? Simultaneously. So we want to, oops, create a two-dimensional grid. A two-dimensional grid is a way of looking at all the sample spaces, and we can do that by drawing it out. Now, a two-dimensional grid. Two-dimensional grid, there's an example here, but we can look at it as an X and Y axis. Two dimensions for this one would be first dimension, tossing the coin, second dimension, rolling the dice. A coin has how many possibilities? 2. Exactly. So we have 1, 2, that's heads and tails. And then for rolling a die, we have how many possibilities? 6. So we do 1, 2, 3, 4, 5, 6. So the grid says we draw lines up top and lines across. And wherever they cross is where an event could occur. So with this, we have how many possibilities? Well, it looks like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possibilities. Okay? And on a tree diagram, you can see that as well. Hopefully, we'll get to that later. Okay? This is an example from your book. So I believe there is... It says there are 12 members in the sample space. Hey, that's what we just set up here. And here's our little grid. Okay? So the first one says tossing a head. Okay? Does the other die... Does the die even matter? Well, let's take a look. We have the probability of tossing a head. There are 2 possibilities. Either heads and a number 1 through 6 or tails and a number 1 through 6. And so our head, tossing a head with this particular thing, is 6 over 12, which is 1/2. Okay? Now the next one, getting a tail and a 5. Now this is the example that they showed right here. Getting a tail and a 5, we actually counted up on our little grid. So we have 1, 2, 3, 4, 5, 6. And then we have the next one, a 5 as well. So that's 7. So we should have... Did I get that wrong? Oh, getting a tail and a 5. Oops, I said or. Tail and a 5. It's not the example. This is a tail and a 5. We would get both of these. It would be just a tail and a 5, which is tail and a 5. Why is it probability of 1/12? The probability of getting a tail. Oh, a tail. God, it's right there. You're probably all going, oh, duh. Sorry. A tail and a 5 is right there. We have 1/12, of course. And the next one is probably going of a tail or a 5. That would be our 7/12. Okay? The enclosed points, whatever that means. Okay, so we have all of the points right here. So if we were to write out the probabilities here, tail would be tail in 1, tail in 2, tail in 3, tail in 4, tail in 5, tail in 6, and then a head and a 5. Those would be our 7 different possibilities. This is example 7 in your book. Okay? So we can keep going on. And now we have another example. Hey, how about you do the same thing, but now it's an outcome table. Now, we talked about an outcome table a little bit. And an outcome table is basically the exact same thing as this, but instead of writing a dot, we write the actual outcome happening in that spot. So instead of writing a dot, we would write T and 1.
Why?
T2. It's just a way of showing that these are the outcomes that can happen. Okay? So for this particular one, we have... Draw a table, okay. Let's see. 2 dice are rolled, and the scores are added together. Okay? So we roll, and we say we get a 1 and a 1. 1 and a 1 is 2. So we take our, I think it's right here. There it is. So here's our first line of possibilities, and our second line of possibilities. Okay? And so a 1 and a 1 would be a 2. And a 1 and a 3, or excuse me, a 1 and a 2 would be 3. We're adding up each of the possible outcomes. It works really well with numbers. Okay? So with this particular one over here, it would have been not adding them together, but the possible outcome. Like 1 and T, 1 and H. Those are the outcomes. So if yeah. Just let you know, I am recording as well, so you're going to be on the audio. Okay, so you can see that our question really is determine the probability that the sum of the dice is 7. Now, 7 on dice happens to be the one that's most common. And when you're playing a game of craps, you don't want to roll a 7. If you roll a 7, the board clears and you lose all your money. Okay? You do not want to get that. You want to get like snake eyes. You want to get, you know, the number you bet on, really. 6s are good. 3s are the best. Anyway, the harder it is, the harder it is to get it, the higher the probability, or the more money you get. So the probability of getting a 3 is really low because it's 2 out of the entire system. And we look at this system and we say, okay, that's 3, or that's 6 this way, 6 this way, that's 6 by 6. You multiply it, that's 36 different ways. Okay? So that would be our universal set would have 36 different numbers. Okay? That would be n of u. And n of u is 36. Okay? It says determine the probability of the sum of the dice here. 7. Well, the sum of the dice 7 is right here. We count them 1, 2, 3, 4, 5, 6. So we say that the number of the event that we want to occur is 6. So now we take that and we divide it. So 6 divided by 36 is going to be 636, which reduces to 1 over 6. Let's check our work from good old-fashioned book. Of the 36 possible combinations, we have 6 are the possible answers. And there's a little 3-dot thing again. Remember, this, I'll just keep pressing that button. This right here means therefore. So, this was something for you to do on your own. How about the sum being 10? Okay? Yeah, 3 by 36. We have 3 of them. There's 1, 2, and 3. So we have 3 over 36, which reduces down to 1/12. Yeah. Okay? And for this particular probability, we're leaving it as fractions. I would say okay with fractions. If I ask for a decimal, please add a decimal. And if I ask for a percentage, you better put your percentage signs. Okay? Alrighty. So this one you can do on your own if you want to pause the video. Well, too late. I already gave you the answer. I already gave you the answer. Okay, moving on. So now we are in section D. D is compound events. Compound events. We've seen compound events. And here's our little example over here. We're going to consider the following problem. We have box X contains 2 blue balls. Here's our little box. And 2 green balls. And box Y contains 1 white ball and 3 balls. I got this example, and 3 red balls. I got this example from the book, so you can follow along with that as well. It's toward the top of section D. A ball is randomly selected from each of the boxes. Determine the probability of getting a blue ball from X box and a red ball from Y box. Okay? So here we go. We're going to dip our little hand in here, and we're going to randomly select a ball. And we want to know the probability of selecting a blue, and we want to know the probability of selecting a red. Now looking at it, we can think, oh, that's a pretty good chance. Well, here's what they did here. They selected to use a 2D grid. And they wrote box Y on the side right here and box X on the side right here. Okay? Now for the blue and the red occur a certain amount of times. Okay? And we can draw it, and we can see that red, blue, red, blue, red, blue, red, blue, red, blue, red, blue. We have 6 different possibilities for that value. So here's what we're going to write. The probability of a red ball being selected, or let's start with a blue ball. The blue ball being selected and a red ball being selected. Okay? So we write the number of that particular event. Okay? So the number of that event on top, which is A, capital A, and the number of the universal set. Well, let's take a look at the universal set, the sample space. Sample space would be 4 by 4. So 4 times 4, we can see that there's going to be 16 different possibilities. Of those 16 different possibilities, where does the red and the blue occur? Well, it occurs 1, 2, 3, 4, 5, 6 times. Okay? So we can take that, and we'll go ahead and reduce it. And I don't mind if you get a decimal or not. Let's go ahead and reduce it to get a reduced fraction, I believe, is 3/8. Okay? So we have 3/8 here. So there's a 3/8 chance, which is pretty close to 50%, but it's actually less than that. 3/8, what's our value for 3/8? It's like 475? Did you get that? 375. Close. Early, very close. So we have a 37.5% chance. Not as close to 50% as I thought. Okay? But this and right here, we can use it. Now, we know that B or R, if we looked at the probability, would be the probability of B plus the probability of R. What we're going to find here is, oh, keep going. I anticipated all of this that I wrote here on this next page. Here's what I think about that. Poink. Oops. Dang. Okay, undo that. Keep going. Let's go ahead and keep going. This and symbol right here, so we have the probability of them and are going to be on the next page. So we have probability of B and R occurring at the same time can be written as the probability of B times the probability of R.
Multiply it?
Yeah. Do you want to test it?
Wait, I don't understand.
Well, let's test it out. This says that our answer right here should be 3/8, right?
Okay.
So we're going to take this, and we're going to instead take the probability of B. Probability of B is 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 out of 16. And the probability of R is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 out of 16. Woo, there's my home page. So if we multiply this, we multiply the tops and we multiply the bottom. And what happens? We get 8 16. Well, let's reduce this, right? Because that's 1/2. So we multiply the top, we get 12. We multiply the bottom, we get 30. Ooh, 36. Can we reduce that?
Yeah.
By 4, right? If we reduce it by 4, we get 3 over, because it's 32.
Oh.
3 over 8. Whoops! Okay? So it turns out that it multiplies, and reducing it, we get it. We get a correct answer. So sometimes it will be easier to, instead of going and making a grid, we can instead write the probability of B times the probability of R. That's a big important thing. Okay? All right.
Oh, wait, if we don't make a grid, how do we know that there's like 4 versions of R? I mean
Goes back to this right here.
so you just multiply like R times 4 and then you get 12.
Well, the probability of, well, if we reduce this, we end up getting 3/4, right?
I got it. I got it.
Okay.
I got it. I understand that.
It's funny because I should have reduced this. This should have been 1/2 times 3/4, which is 3/8. That's easy enough. But look at this. This is 1/2. B is 1/2 of this particular event. And this is 3/4 of this particular event.
What?
Holy buckets. We get 3/4. All right. So let's see, where are we? I kind of jumped ahead. So we're talking about independent events now. Where are we? Compound events. Still in section D. Independent events. Independent events. So what is an independent event? This occurs, so our events are independent of one another if they do not affect the probability of the other event. Okay? So we take our, it says consider the ball example again. So let's go ahead and delete this. So let's define first off what probability is of independent events. Definition. This is events are independent. So two events or two or more events. Two or more events that occur.
Independently?
Okay, I don't want to define it by using that occur and do not affect each other. That's it. They don't affect each other. Okay, so actually I'm going to create an example here. Suppose I had a bag of jelly beans again? Okay, a bag of jelly beans again. So we have green jelly beans. 1, 2, 3, 4. We have red jelly beans. 1, 2, 3. And then we have blue jelly beans. 1, 2, 3, 4, 5, 6. Yeah, white jelly beans. That'll turn out great. So we place our hand in there, and in later mathematics you call this with replacement or without replacement. You dip your little hand in here with all 37 fingers, and you pull out let's say you pull out a blue one. Okay? So this event says that you have a 1, 2, 3, 4, 5, 6 out of 6, 7, 8, 9, 10, 11, 12, 13. 6 out of 13 chance. It's blue. Okay? Now, suppose you didn't replace it, and you reached your hand back in, and you want to see the probability that you'll pick a blue. Now, we have to decrease it by 1 because you've already taken one out. You know what? You ate it. It's no longer able to be there. Okay? You ate it. So this means that you're not replacing it. Okay? That is the definition of an independent event. That you actually put it back. Okay? You put it back because you want it to be independent of another. You want to say, okay, I take it out and I go, oh, I got a blue. Let's see about that again. Put it back in. Ooh, I got a green. Ooh, let's see if I can do that again. You put it back in. Okay? You have to replace it. There's replacement. Put it back. And share. Okay? Sharing is caring. All right.
Hands all over it.
Yeah, you got your dirty little mitts on it. That's true. Probably going to get like Ebola or something like that. Maybe not Ebola. That could be a little dangerous. So dependent. Oh, wait. So that's independent events. I kind of just described what dependent events are. They depend on the previous event that happened. Okay? So, I'll go ahead and stay consistent with my slide, and I'll say the definition of a dependent event. A dependent event is when one event occurs and the following events are affected. And it's compounded. So we go back to our little jelly beans. Okay, let me see if I can select this. Nope, select it. Nope, select it. Okay, copy. Paste. 3 somehow got involved in that, but that's okay. So we go back. We take out a jelly bean. And it's green. Oh, it was a 4 out of 13 chance. Now, we cross out one of those jelly beans. Heidi ate it.
Yes, I did. And it tasted good.
Like boogers. It's green out of all of us. No. So now, we reach our hand in. So that was the first.
Take any red vines out of it.
Yeah, red vines. So that was our first event. The second event occurs. Dip our hand in. We pull out a red. So this green occurred. We pull out a red. Ooh, red occurred. Now we think about this. We have to do the number of occurrences for red, so that's the event A, over the number of our universal set. But guess what? Our universal set has changed because Heidi ate one of the samples. So now we end up with 3, and this is down to 12. Oh, dang. Okay, so this is 3 out of 12, which is a 1/4 probability. Let's look at the next one. Suppose, wait a second. Oh my gosh. Caleb ate that red one. It was cinnamon. Lucky him. That's a good one. I'm actually allergic to cinnamon. So Caleb ate it. Oh, dang, it's no longer there anymore. But Sarah pulls out another red. What are the chances of that? Well, find out. We have, how many reds are left? 2. How many jelly beans are left? 11. So now we have a 2 out of 11 chance. And so on and so forth. Okay? Those are called dependent events. They depend on the previous one. Okay? Oh, good. We're already on section E. We only have 2 more sections left. We got 40 minutes. Excellent. I'm going to take my time. Just joking. Okay, so using a tree diagram. So let's go ahead and I should have given you guys an example.
Didn't you already teach us how to do this?
Yeah, but I'm going to teach you an example. Oh, I forgot to mention. I'm sorry. There was another slide in here that I wanted to... Where's my little cursor? There wasn't another slide in here. Oh, did I run out of batteries? Wake up. That would be really, really bad. There we go. Atta baby. Okay. So one other thing that I wanted to do, because I talked about independent events. And independent events, we can use this. Now, this is for independent events. I totally forgot to mention that.
That formula?
Yes.
Probability in the end.
Independent events. B and R. Okay? We can say that the probability of 2 events occurring... give it just here. I'll take it. Thanks. So the probability of these events happening for dependent is different. Okay? Because we can't say, okay, I take out a B and then it's the same, take out a B. Take out a red one and then we can take out a blue one. They're going to change. Okay? So what we need to say is that we're going to select all this and delete it. And we're going to go ahead and write a formula. And that is the probability of it's a probability of A, then B. Right? You pick A, pull it out, and then you pick B. They are dependent on one another. So that turns out to be the probability of A times the probability of B given. that A has occurred. 2 R's? Yes. Occurred. You gonna head out, Madison? Okay, see you later. All right, so let's go back to our little possibility over here. So we're trying to find the probability of A. I wanted to go back to that particular example. With a probability of A, we're going to call that pulling a, what was it, blue? Let's see. It was a green jelly bean. It was 4/13. So pulling a green, and then pulling a red. See you later. A red. So pulling a green turned out to be 4 out of 13. Okay? But we want the probability of both of these events, A then B. So we have to multiply that by the probability of pulling a red after we've pulled the green. So we look at that and we say, oh, it was 1/4. So we multiply it by 1/4. And we get a number of 4 over 13 times 4, which is 52. And I know that's divisible by 4. And it goes in 13 times. 1 over 13. So, if we wanted to figure out the probability of dependent events and both those events occurring simultaneously, not at the same time, but one after another, we say, okay, what's the probability of both of them happening? Well, we take one that's 4/13. We take another one. That would be 3/12, which is 1/4. And then we multiply them. And we end up getting the probability of doing that both simultaneously is 1 out of 13 chance. Okay? For independent, if they were independent of each other, that would be different, right? We would take, so independent, this is a little side note, independent would be 4/13, and then B. So we're saying probability of A and B occurring, or A then B with replacement. That would be 4/3 times whatever B was, which is not 1/4 anymore. It would be 3 over 13. Does that make sense? Okay. And we end up getting a larger number, 12 over 169. And so the probability of this then, so A then B occurring, is different than the probability of A then B occurring given that A has already occurred without replacement.
So it's saying that those things would happen like next to each other, right? But one's with replacement and one's without replacement.
Yes, so I'm saying like this is a different example. So suppose so here's my little bag of jelly beans, okay? I'm saying that a dependent event says once we pull one out, it's gone. The next one, it's gone, okay? And we want to know the probability of those events occurring in one set probability, okay? Independent says we put them back and we take one out, and then we put it back in. Or we replace it with exactly the same thing. That's called the replacement part. Okay? Excuse me. Okay. So, good. And it affects. I've been spelling it effects. It affects. Terrible at that. Okay, so the tree diagram, it's interesting. Tree diagram, let's go ahead and go down here. And we're going to look at the heads or tails option, okay? Bam! Oh, there's the question. Okay, cool. Just showed up. How spontaneous is that? Okay, so it just showed up. Now, we have car or car not happening. Now, we need to write in what are the possibilities of that happening. Well, the possibility of the car starting, it says it only starts 80% of the time. So we write 80% in decimal form is 0.8. Now, if the car does not start, then what would our probability be? 0.2. We have to add up to 1. Okay? These are compound events. So that's how it works. I think it's compound, not complement. No, it's complementary events, not compound events. Excuse my language. Complementary events. There it is. Okay? So now we go over here and we say, okay, so instead of our toss, we're saying our first start is that. So now we're going to see his motorbike. So motorcycle start. So for each one of these car starts, it either starts or it doesn't. So we say it either M's or it M primes. Okay? This one, it either M's or it M primes. Okay? So I'd like to separate these out a little bit. There we go. So we have to figure out exactly what the probability is for those. Well, it said 60% of the time. So we say 0.6 it starts, 0.4 it doesn't. 0.6 it starts, 0.4 it doesn't. Okay? So each one of these is dependent. So we look at that and we say, oh, okay. If that's the case, not dependent. These are independent of each other, but our probabilities, we have to calculate that. So for this probability right here, it would be the car starting and the motorcycle starting. What is the probability of both of those starting? Well, we take 0.8 and we multiply it by 0.6. Why can't we just multiply it right across the bat? Because they're independent events. So this is for independent events. And we end up getting a number of, I think, 0.48. So that's a pretty good chance that it's going to start. About 50% chance that both of those are going to start. What about our other one right here? Well, that would be 0.8 times 0.4. Now, what is it saying? That's saying if the car starts and the motorcycle doesn't. So we end up getting 0.32. So there's a 32% chance that will occur. So suppose the car doesn't start and then the motorcycle starts. Well, that would be 0.2 times 0.6, which is 0.12. And suppose the car starts, or the car doesn't start, and the motorcycle doesn't start. That's 0.2 times 0.4, and we end up getting 0.08. What occurs here? Well, if you add all of these up, this should equal 1.00. So it says, draw a T diagram to illustrate the situation. Use the tree diagram to determine the chances of that both will start. So we just did that. Car starts, motorcycle starts, it's a 40% chance. Okay? 0.48 probability. It says, Carl can only use his car. If Carl can only use his car, that would mean the car starts and the motorcycle doesn't. And then the car starts. Yeah, just the car starts and the motorcycle doesn't. Okay? So he's out there, he's like, okay, I'm going to try them both, see what happens, turn the car on, it works, turn the motorcycle on, it doesn't work. So that gives us a 32% chance that would occur. Both. I personally think in percentages. I don't think in probabilities. A lot of people think in percentages easierly. That's not a word.
So if it asks you for the probability, would you
If I say, what are the percent chance, I want percent. Otherwise, decimals. Yes. Decimals, unless I say otherwise. So that's the tree diagram. And let's look at, I believe a T diagram. A T-diagram can be used to illustrate sample spaces if the alternative are not too numerous. Okay, you don't want to get too big. If you want to have like 75 different outcomes, a T-diagram is not going to actually work out. Once the sample space is illustrated, the T-diagram can be used to determine the probability. Okay. In this section are independent events. So I think I'm going to save F for later. F for later. I'll start. What day? So next time, Friday. Start Friday with this. So your homework, delete, is, here they are. Let's go ahead and type them in. I want you to, I wrote it in the book and okie doke. And that's it.